again. Okay, so now we're going to start chapter 15, which is another kind of carbonyl compound that has different reactivity than we've seen before. Okay, so the first thing I'm going to do is share my screen. Let's see if my iPad will behave today. Come on. Nope, not that one. There we go. All right, I hope everybody can see my screen. Let me move all of these over here. All right, so that's good. I am presenting and I am recording. All right, great. Go ahead and somebody ping the chat box, make sure that's working for me, please. Okay, so what we're going to talk about now is what we call enolate ions, okay? So the key here is we actually have to remove a proton, the most acidic proton in the set, and then we can use that removed proton to act as a nucleophile. Or I'm sorry, not the proton itself, but that spot that we removed that proton as a nucleophile to do other reactions. But the first thing we have to do is define what alpha hydrogens are, how it relates to carbonyls, and what changes the acidity. Okay, so that being said, okay, whenever we talk about the concept of alpha hydrogens, remember when we looked at those common names for esters, we called that first carbon over from the carbonyl the alpha carbon. We're going to use that same nomenclature to define our alpha hydrogens on this thing, in this chapter, okay? So the first thing we look for is our carbonyl. It can be any kind of carbonyl. It can be an ester. It can be a carboxylic acid derivative. It can be an aldehyde or a ketone. The key here is that we have to have hydrogens on a carbon next to a carbonyl. Okay, so in the case of this compound we have right here, we actually have alpha hydrogens on this side of our ketone and alpha hydrogens on this side of our ketone. The key is those are both hydrogens that are one carbon over from a carbonyl, and they have hydrogens on them. I'm being very specific about adding hydrogens to them because there are several of these species we'll use where they don't have hydrogens next to them, and that means we can use them in a very specific way. So the key here is to look for hydrogens that are on the carbon next to a carbonyl. So in this case, aldehydes should only have one carbon with hydrogens on it. Ketones will have two carbons with hydrogens on them, like the species here. Esters and other things should only have one carbon that has alpha hydrogens on it because of the other bonding on it. And I'll show you a couple of those in a minute, so keep with me. Okay, so the reason we can call these acidic hydrogens is because of resonance stability, okay? So in general, you would think an alkane hydrogen is not very acidic. An alkane hydrogen, if you'll remember our pKa for ethane, the hydrogen on ethane is like 50, which is like the least acidic thing we have, okay? However, if we blow this compound up right here, the fact that if we take these electrons away from that sigma bond and put them on this carbon here by interacting it with a Lewis base right here, what we'll end up doing is we'll be creating an anion on that carbon. However, because of resonance, that anion does not stay on that carbon, okay? So we should start looking like, remember in the chapter with ketones and aldehydes, we had that eno-keto tautomerism, okay? You should start seeing that, but instead of being neutral species and moving a hydrogen, we actually have a charged species. In that same tautomerism, and it comes up as a resonance stabilized enolate ion, okay? So what we're seeing here is that when we first form it, the negative charge is on this carbon here. However, we can move electrons back and forth and have it stay on this oxygen Maybe most of the time, maybe some of the time. But once it goes back to being on this carbon here, it is the stronger of the two as far as being a nucleophile. The carbon nucleophile that we form here is stronger than the oxygen nucleophile that we generate here, meaning it's going to do the next reaction, okay? So the reason they're acidic is because of resonance stabilization. Their location, one carbon over from the carbonyl, is required for that resonance stabilization. Okay, so if we only have to have a hydrogen on a carbon next to a carbonyl, what kind of structures can we use for that? We can use a wide number of structures here. And so let's start with one of the more simple ones. Let's look at the middle of the road here at our ketone, okay? So our ketone has a CH3 next to a carbonyl here. In the case of this right here, we have a different structure. That's a diester that we'll look at again. But again, we have a hydrogen next to a carbonyl. In fact, this is next to two carbonyls. So that's going to bring it about something very interesting there. We have this hydrogen, which is also next to two carbonyls. We have this hydrogen next to two carbonyls. So we have a wide variety of structures, including esters, where we have a hydrogen on the carbon next to a carbonyl, okay? So now that we have a wide variety of those structures, let's rack and stack them as far as increasing acidity, okay? So let's go back to what we know about some of the things to get us kind of started. And the first thing I want to draw our attention to is water. Okay, our pKa of water is about 15.7, and we know that water can act as an acid or a base, right? So we want to like compare everything to water, okay? So alcohols are just slightly less acidic, followed by ketones are less acidic. Then we have esters, and then we get up to our first hydrocarbon. Our first hydrocarbon is an alkyne. Remember, that's the one we can remove with sodium amide, and that's up here around 25. And then, of course, the alkenes and alkanes are even less acidic than that. Okay, so let's start looking at our carbonyl compounds. When we have a carbonyl compound with an oxygen donator, right here, so we have a carbonyl, in fact, we have two carbonyls, and we have two electron donators. It's still more acidic than water. However, we can get to more and more acidic systems, okay? So we look at this, this is what we call a beta diester, meaning we have two carboxylic acid esters that are bridged along that alpha carbon, okay? So this is our alpha carbon, and that's why we call it a beta diester. If we take one of those esters away, which has that electron donating oxygen, and put a carbon there, we now have what we call a beta ketoester. Notice we have a carbon on this one and an O ET or ethyl group there, okay? That makes that hydrogen more acidic because this OH here is donating electron density. We've taken that donation away. That means that hydrogen now became more acidic. Now, in the case of phenol, it's not a beta keto compound. It's just there for comparison because, remember, it has resonance stability too because it can donate electron density to the ring, okay? And the strongest of the set is what we call the beta diketone. Notice it's got two carbonyls, but there are no oxygens on there. And so this is the most acidic of the compounds we will be using to make enolates, okay? So we have the alpha carbon right here, has two carbonyls on it, making it the most acidic hydrogens we can use. Okay. So that being said, let's go ahead and talk about the conditions required, okay? So if we look at the acidity of that hydrogen for just a ketone like this, we saw from the previous scale, it was approximately 20, okay? So that means we have to use a strong base to form that enolate. And in the presence of that, we should get our stronger acid turns into our weaker base. Our stronger base turns into our weaker acid. So if we look at the pKa of the conjugate acid formed, it's higher, right? We have a A pKa of that ammonia is 38. 38 is higher than 20, therefore 20 is more acidic. That means this is a strong enough base to remove a hydrogen from this ketone. Okay. When it does, it'll create this resonance stabilized enolate anion. Okay. Now, in comparison, we showed you that beta diketone compound had a much higher acidity, had a pKa of 9 right here, which means we can use a weaker base to pull off that proton. In this case, we're using sodium hydroxide, which is a weaker base than sodium amide, but it's a stronger base than the enolate ion formed. And when we take hydroxide, sodium hydroxide, and turn it into its conjugate acid, that turns it into water, okay? So when we have our hydroxide here converting to our conjugate acid, we have water. And if we compare the pKa of water to the pKa of this beta diketone, we see that water is now the weaker acid. Okay. So key here is we have to use a base that is the correct strength for the acidity of the alpha hydrogen we're looking for. Okay. So what we'll see is based on how on different structures, we can use different bases. For things like ketones, we have to use a very strong base like the sodium amide bases. Once we go to the diketone compounds, we can start using hydroxides, and we might even be able to use some weaker bases later on. Okay, so let's say how this works, okay? So once we form that anion, we can now use it as our nucleophile. Those electrons here are our Lewis base. Here, I'm gonna unshare and share again. It's kind of lagging a little bit from what I'm writing here. Okay, let's see. Okay, so once we form this anion, we now have a Lewis base, right? Because we have electrons that we're willing to generate a new bond with. So if we were to take those electrons and, I'm gonna switch colors to red, attack our carbonyl. Now remember why we're attacking our carbonyl. This is partially positive, this is partially negative, and so therefore our negative charge is attacking our partially positive carbon. And when we do that, we generate our new sigma bond and a charged species, okay? So this is our intermediate, and that's the first thing that happens, okay? Now that charged species, because we formed a carbon-carbon bond, is pretty stable. It's gonna wait around until it gets protonated, okay? So that's the first way that enolates act as nucleophiles on carbonyl compounds. Was the top part of the ketone supposed to be partially negative? Okay. Oh, yes, you are right. That is, let me erase that. Again, my pen is lagging a little bit there. So the oxygen was partially negative. When we generate the new sigma bond, it is now fully negative. Okay. So that's what happens when we have that enolate ion attack a ketone. It creates a new carbon-carbon bond, and we have a stabilized thing because the only leaving groups we now have would be R-, okay? And we know that R- is not a very good leaving group. But if we do it to something else that has a better leaving group, we might actually see something fall apart, okay? So that's why I want to draw your attention to the next one right here. So let's say we create an enolate again. We use it as a nucleophile, and instead attacking a ketone, like up here, we're going to do an ester. It has the same thing. The carbon is partially positive on the bottom. The oxygen is partially negative on top. And that what we'll do is we'll create this intermediate because we form this new carbon-carbon bond here. However, because of this intermediate, we actually have a really okay leaving group. Okay, so we use some very strong base like sodium hydroxide or something to make our enolate ion. Well, we can actually have that alkoxide leave as the weaker base, generating a different product. Notice that here we stop the reaction and have the anion be stabilized. Here we actually lost the anion as a leaving group. Okay, So in some of these reactions, especially when you have something like an alcohol that can leave, we will actually have that leave. Sometimes they're going to stop at this where they've just formed the carbon-carbon bond. Okay, so we need to look at those, and they actually have different names, and so we'll see them as we go forward. Okay, so the first thing I want to talk about is we have a named reaction called a Claisen reaction. Okay, think Claisen is an ester. Okay, it's always an ester. Okay, and when we have an ester, that means we can eliminate one of the alcohol groups to produce what we call a beta keto ester. Okay, so what we have here when we start is this compound here. Notice there's no CHs over here, which means the only place we have acidic alpha hydrogens is on that carbon there. Okay, so what we're going to be doing is we're going to end up making our anion here, and then that's also where we're going to create our new carbon-carbon bond. Okay, but that compound there also lost ethanol. Okay, so we need to keep track of where that ethanol was and why it ended up there. Okay, so let's look at this in a more stepwise fashion. No, this is what we can do after that. Once we've formed that compound, that beta keto ester, we can actually use our saponification or our base reacted ester to form our carboxylic acid. And once we do that, something else can happen now. Because we have two of these close together, we can do that decarbonylation reaction we saw in the carboxylic acid chapter. Now that we have this beta ketone available to us with this carboxylic acid, just by heating it, we're going to lose CO2 and keep our carbonyl compound. So in this, even if we form this enolate ion and do our first reaction to make our beta keto ester here, we can know additional chemistry to lose that, to regenerate a ketone, our new ketone. Okay, the next reaction we have, instead of just using that nucleophile to attack a carbonyl, we can actually use a nucleophile to attack a double bond near a carbonyl. And what we call this is, we call this the Michael addition. Because what we're going to do is we're going to form our enolate here. This is where our anion is going to be. And instead of attacking the carbonyl, what we're going to do is we're going to attack actually our beta carbon here, because this double bond is in conjugation with this carbonyl. Okay, so I'm going to show you on the next slide. Don't worry. So what we're doing here in the Michael reaction is we're actually creating an enolate from something else over here. And instead of attacking the carbonyl, it's going to attack a carbon, the beta carbon. So not the one next to the carbonyl, but the one opposite it. And we can use that with both ketones and esters as long as the double bond is in conjugation with the carbonyl. Okay, so why does this work? Okay, this works because if we look at our resonance structure with our double bond here and our carbonyl here, we can actually use resonance to go back and forth to generate a partially positive charge at that beta carbon, that carbon 2 over from the carbonyl, and a negative charge here. Remember, our enolate has a negative charge. We're forming a partially positive charge here at the end of the chain now, at this beta carbon, instead of using the partially positive charge of the carbonyl. Okay, so when we do it on the beta carbon, or 2 carbons over from the carbonyl, that's the Michael reaction, typically called the Michael addition. And so we're going to be doing several things. We're going to be doing Claisens, we're going to be aldols, and we're going to be doing the Michael addition. But they all start with the formation of that enolate ion. Okay, so when we have Michael reactions, we have to have two things. We have to have something that has a carbonyl and a double bond in it. So we can have aldehydes, ketones, or esters. And we typically use something that has a dicarbonyl compound in it. So that could be a beta diketone, a keto ester, or a diester. And occasionally, we can use amines as the base to do this reaction. And I'll show you that in the next set of slides. All right, questions on the concept of what alpha hydrogens are and why they're acidic. Okay, so I'm going to go through each and every one of these reactions separately in goal 2, but I wanted to show you how to recognize alpha hydrogens, how to rank and stack their acidity based on how many electron withdrawing groups or carbonyls are nearby, and some other things that can happen in the reaction. All right, so I'm going to go ahead and come out of this one and go to goal 2, the reactions. Okay. In the goal 2, the reactions, we're going to actually go through. Several of them have different names. There we go. Several of them have different names. And if you keep track of the functional group used for each name, you'll be able to see a similarity here. Okay, so each name means you're starting with a different functional group. Okay, and therefore you might end up with a different product. So keep track of that, okay? And I'll try to draw your attention to it as we go. Okay, so in all of these reactions, we're using that negative charge here to turn our carbon into our nucleophile, and we're always going to be making a carbon-carbon bond. Okay, that's the key to all of these reactions, but they have different names because we start with different features. Okay, so the first thing I want to talk about is the aldol reaction. Okay, and in the aldol reaction, it was originally used with aldehydes, but it then got moved to ketones. And the key with the aldol reaction is you end up with an alcohol and a carbonyl. Okay, so think aldol having all at the end means you end up with an alcohol at the end. Okay, so the basic reaction is that you have to have something with an acidic proton. In this case, our aldehyde only has one side with acidic protons. In the case of our ketone, we actually have a choice. Okay, and I'll teach you how to choose which one. Once you form your anion here, what's going to happen is it's going to react with another one of itself and open up the ring to give you a alcohol on your beta carbon. Okay, I want to draw attention to this bond right here. Okay, this is the new bond created by the anion on one end and the carbonyl on the other side. Okay, so the carbon with the alcohol on it is the one that the carbonyl was attacked. The side of the molecule with the carbonyl in it is the one that you made the enolate out of. And I'll show you the mechanism on the next slide. Okay, so we can do that with the ketones as well. You make a enolate on either side of here, then either side of this attacks the carbonyl on the other side. And so this is the one that had the enolate on it. And this one circled in red is the one that was attacked as the carbonyl. Okay, so the one that was attacked with the carbonyl has the alcohol on it when you're done. Okay, so how does this work? Okay, so the first step in all of these reactions is to remove a proton. Okay, that's one of our 5 common ways to do a mechanism, right? The first thing we're going to do is we're going to use a strong base to remove a proton and create our enolate ion. The next thing that happens is our enolate ion will react with the carbonyl carbon, and this is the wrong structure, I'm sorry, this is the wrong structure here, will react with the carbonyl carbon. Let me just draw it over here. So we have an unreacted species here,
CH3. We formed an enolate here. And so the electrons from this enolate are going to come in and attack here, kicking this open, giving you a charged species on this oxygen, okay? So let's look down here at this structure here. So the product of this reacting with this gives us this compound here, okay? So notice that this side right here is the one that the carbonyl was on. This carbon here is the one with the anion here. And so the intermediate is this charged species. Then this can act as a base and deprotonate something like water and regenerate our neutral species. And this is, of course, our alpha carbon. And so this is our beta carbon. So this is our beta hydroxy ketone. Let's see if I have that other step there. No, I don't. Sorry. I don't know where that figure went. I hope it's in the video. Okay. So in the case of the aldol condensation, we use a compound that we use the same compound on both the making the enolate and the species that gets attacked, okay? So the basic aldol, we take one equivalent here, we make the one of them into the enolate, and we react that enolate with another one of the same species. That's the aldol reaction here, okay? What if you wanted to be very specific about your reaction? And the way to do that is do what we call a crossed aldol reaction. In a crossed aldol reaction, we have something that has alpha hydrogens, and we have something that doesn't have alpha hydrogens. Notice this species here has a carbonyl, but no alpha hydrogens. Okay. What that means is we can only form our enolate from this thing. Once we form our enolate from this thing, it will only attack this. We get a much more specific reaction. But because this is an aldol reaction, we still make a beta hydroxy ketone. But we only form one possible product, okay? So the first step is, of course, forming our anion here. Again, no alpha hydrogens, we can't form an enolate here. We have attack by those electrons to the carbonyl, generating the salt of our alcohol here that when we add acid to it, we get our free alcohol back. Okay. So an aldol is reacting half of the reagent with base to form the enolate, and then it reacts with itself. The crossed aldol is where you take something that doesn't have alpha hydrogens and you attack it with another compound that you made the enolate out of. Okay. So aldol and crossed aldol have the same product of the beta hydroxy ketone, but you can use different reagents in the crossed aldol. Okay, so we also have an opportunity if we have a compound with two carbonyls on it. The possibility we have for that is that we have the ability to pull off our alpha hydrogens to make our enolate here, but we have another ketone somewhere else on the species, which means we can actually have it wrap around and attack itself, creating a ring, okay? This will only happen if you can form 5 or 6 membered rings. 4-membered ring is too small, 7-membered ring is too disordered, so it has to be a 5 or 6-membered ring to form them specifically. All right. I got a lot of lag here for some reason today, but the key here is that if you have 2 carbonyls in the same molecule, you will be able to close a ring if it's a 5 or 6-membered ring. And goal 3 is actually, I'm going to show you where to look for rings and how to show them. So I'm not going to do much more on this, but I want to know that this is goal 15, I'm sorry, chapter 15, goal 3.
will be all about these ring species. Okay, so if the aldol condensation involves ketones and aldehydes and generates a beta keto alcohol, the Claisen involves esters. Okay, so aldol involves aldehydes and ketones. Claisen involves esters. Okay, in a simple Claisen, which is where you take two equivalents of the same material and half an equivalent of base to react with itself, we end up with what we get is a keto ester. This should be a beta keto ester here. Okay, so aldol, we got a keto alcohol. Claisen, we get a keto ester. Okay, now let's figure out how this reaction works. Okay, so the way this reaction works is that we start with, notice these are exactly the same compound, just drawn differently, right? We have ethyl propionate here. We're going to remove a proton from here. Okay, if we remove that proton from there, that turns this into the enolate ion, which is then going to attack here. And instead of generating an ion right there, we're going to lose ethanol to generate our new species right here, which is our keto ester. So ketone on this side and ester on that side of our material. Okay, so first step is form our enolate. Then we react our enolate with the carbonyl compound, losing alcohol to generate our new sigma bond. I'm going to draw our new sigma bond in red here. This is our new sigma bond. We've lost our ethanol here. And so we end up with our species of ketone plus ester. All right, so that is the Claisen reaction. Claisen reactions always use esters, and therefore you can only take the alpha proton off one side of the carbonyl. So that makes it easier to figure out where the products are going to go. However, in the Claisen, you also lose one equivalent of alcohol, which is the other half of this ester here. So we end up with a beta keto ester. Okay, so let's look at the mechanism of that. The first step is to remove the proton from the side you can remove the proton on. Remember, this side, we don't have an alpha proton. We know exactly where we're going to form. We're going to get our resonance stabilized anion here. Okay, that's just going to make it more stable and easier to make. But this is still our nucleophile. The carbon is still a stronger nucleophile than the oxygen here. So the carbon is going to do the attack. Okay, so here we go. We've redrawn our nucleophile, our carbon nucleophile, and it's going to come in and attack the partially positive side of our carbonyl, giving us our intermediate species that has the charged oxygen and our neutral sigma bonds for the rest of the molecule here. Okay, so we have a couple things that can happen here. A couple of things that can happen here would be the electrons from the negative charge come in to form a double bond. Then it has to kick out the most stable anion. Okay, now I say most stable anion because if it kicks this out, that's a carbanion. We know that was not very stable because that is what we use to make this. If we kick out this one, that's not very stable because this is the actual compound we use to attack it. So that means this actually makes the most stable leaving group as the alcohol salt or alkoxide. Okay, so when we have that ester there, that means the alcohol portion of the ester is the best leaving group. And so we end up creating our new sigma bond right here in red. And then we have that leftover alkoxide salt, which then when we, it is actually strong enough now that we have a diketone compound, a
carbonyl compound to deprotonate that in between. Remember, when you have a single carbonyl, that's an acidic alpha proton. But when you have two carbonyls, that makes that proton even more acidic. So that strong base reacts to form this compound here. Okay, so there's a couple cool things about this compound. Because number one, it's resonance stabilized because we can move that anion up here and here. Or we can also attack other species with it because it's still a carbanion. But if we take that and react that with water, we get to our neutral species here. And again, we have our ketone side and our ester side. Where to go? Our ketone side and then our ester side. So our Claisen gives us the keto, beta keto ester. Okay, so can we do a cross Claisen with that? And the answer is yes. The way you do a cross Claisen is you use something that only has alpha hydrogens on one side of the carbon, on one of the substrates, okay? So that means we can't have a regular ester. We can have formates right here. Notice there's no CH3 here, which would make it an acetate. Those would be acidic protons, okay? Here we've done what we call a carbonate, which is a double ester on a carbonyl. And here we have also another compound with no alpha hydrogens. Notice there's no alpha hydrogens here, okay? Anytime we say crossed reaction, like a cross Claisen or a aldol, one of the other compounds does not have alpha hydrogens, okay? And in the case of the cross Claisen, it's an ester with no alpha hydrogens. Okay, so what are the steps in that reaction? Well, it's kind of the same thing, except now we can only form the enolate on one of the compounds, okay? Because we can form the enolate only on this compound, that means this is only going to react here and kick out only this alcohol, leading to our nice clean product of our ketone side and our ester side here. Notice the ester is always on the side that had the acidic proton. The ketone is always on the side that had no acidic proton. So again, the ester without alpha hydrogens ends up as the ketone. The ester with alpha hydrogens ends up as the ester. So that's a great thing about cross Claisen, an easy way to tell which side of the reaction it's going to end up on, the aldehyde, sorry, the ketone or the ester. Okay, so in both of the aldol condensations and the Claisen condensations, we end up forming a new carbon-carbon bond. And in both of the reactions, we end up with an ester. And now, because we have an ester, and because we have a beta carbonyl compound, we can again clip off this alcohol and heat it up with acid to form that six-membered ring to give us our, that's oxygen, our six-membered ring, which means we can decarbonylate here. So whenever we have a beta keto ester, we can always hydrolyze off the ester and remove the carbonyl, which is what happens on the next step. Okay, so for both the products of the aldol and the Claisen, we can do the thing where we remove the ester group, giving us the carboxylic acid. And of course, if we rearrange this so that our carbonyls down here and our single bonds here, we can then transfer the hydrogen to the side, the electrons here, and we end up with CO2 and just a regular carbonyl compound. Okay, we're coming close to the end here. All right, now let's look at the Michael addition in detail here. So in the Michael addition, we have something that looks like it has alpha hydrogens, okay? Because it does, it has this alpha hydrogen here and these alpha hydrogens here. These are more acidic than these. However, in almost all Michael additions, we have a dicarbonyl compound, okay? Because we want to make sure we remove the alpha proton that's in between the two carbonyls, which is always this one here. Whenever we remove that, that allows us to do the Michael addition on the beta carbon to give us our beta. And in this case, where we have a ketone here, we have that beta addition to our compound here, giving us a ketone. In the case of having an ester here, notice we end up with our beta addition and we keep our ester. So the Michael addition always has one component has a double bond next to a carbonyl. The other component almost always has two carbonyls on it to make sure you only take away one of the protons. Okay, so what does that step look like? Again, the idea, because we have that resonance stability, we have a partially positive charge at this carbonyl, which can be resonance stabilized to here. That's making this a good place for that compound to attack, to give us our new sigma bond on that one carbon over, that second carbon over from the carbonyl. Okay, so what are the steps in the Michael? The same as before. We remove a proton from one of the dicarbonyl compounds. The nucleophile then comes in and interacts with the double bond. That kicks electrons over to give us a double bond where the carbonyl was and an anion here, okay? So of course, this anion is now resonance stabilized back and forth between these two, giving us our product here. The last step in the mechanism is to transfer a proton from one of the acids to give us our enol form here. And of course, what we know about eno and keto tautomerism is that the keto form is always more stable, and therefore it reverts back to its ketone stage, giving us our nucleophile added not at the alpha carbon, but at the beta carbon. So a Michael addition, it makes a new carbon-carbon bond at the beta carbon to the original carbonyl. Okay, so here's a good example of that. Again, we have the species that gets deprotonated is the one with two carbonyls on it. The species that gets added to it is the one where the double bond is in conjugation with the carbonyl, giving us our new sigma bond at that beta carbon. And it doesn't matter whether it's an ester or a ketone species here. But if we do have a beta ketone compound, we can always hydrolyze off that ester and decarbonylate with heat. And in this case, we'll end up getting this nice symmetrical diketone species. So here we had this diketo ester species. We take away the ester, turning it to carboxylic acid. And then through thermal decomposition, we end up with our diketone compound. Okay, so to summarize, we have the aldol condensation, which always involves aldehydes and ketones. We have the cross aldol condensation, where it always involves aldehydes and ketones, but one of the substrates has no alpha hydrogens. We have the Claisen reaction. That involves esters, okay? And in the Crossed Claisen, that involves esters where one of the compounds has no alpha hydrogens, okay? Then we have the Michael. The Michael has to have something that has a dicarbonyl compound and a double bond in conjugation with a carbonyl. Okay, so those are the three classes and the two, the specific reactions that are called cross reactions to allow you to do that. In our last one, which we'll do tomorrow, we're going to do a summarization of the rings and rearrangements possible in these reactions.
Okay, so I'm going to stop sharing my screen and go ahead and ask if anybody has questions. You can put it in the chat or talk freely. Let me go ahead and stop recording.